Hi guys, and welcome to the second Genome2D DevCast. Sorry for the delay, but I was refactoring some of the materials and renders method to make the custom render implementation as easy as possible. Okay, without further ado, let's start. So what we are going to talk in today's Genome2D DevCast, first we are going to talk about Nape physics integration, because a lot of you were asking me how to integrate with Nape, and there was a somewhat native Nape integration in previous Genome2D. So I'm going to talk about how to add Nape to the current Genome2D, and it's very easy. So you will be able to start in minutes. And secondly, I'm going to talk about custom renderers and how you can implement your own renderers and batching and stuff using the EG renderer interface and how Genome2D handles it internally. You will be also able to implement 3D rotations, for example, through this, so a lot of people are looking forward to it. So let's start with Nape. Before, in the old Genome2D ActionScript version, there was an internal support for custom abstract physics through which you were able to implement Box2D and Nape and all that stuff, which was great, but a lot of people were trying to customize it, and once we had all these abstract objects inside Genome2D, it was rather cumbersome to do that. So I decided, since it's very simple even without the native support to implement it, I decided to clean all the abstract stuff inside Genome2D. So we got even a small bump in performance, very small, it's not even 1% I think, but it cleaned up the code. And there is no abstract physics stuff inside Genome2D now, and you can implement your physics using components. And let me show you. So let's run this small example. What we have here is the standard box is Nape example, and a small floor here. It's not even wide as a stage, so if we put boxes here, it will fall through, or here it will fall through because it's thin. So how to implement this? I created a small example. We initialize Genome2D, that's the old stuff. We create the floor here without using any genome component and stuff. You can always access the low-level Nape API to create your stuff, and it will obviously collide with the internal Genome2D physics, which will be implemented through Nape as well. And we need two components. As you can see, here is the one. It's a Nape physics component, which is very simple. All it does is create the Nape space and then handles the update. So it hooks a callback to Genome2D update handler and update the space of the physics when the delta type is larger than 0, because sometimes we have a delta time which is 0, and Nape would be it doesn't like 0 delta time. So once we have this, we need to create the Nape bodies using the space inside the physics component. So we will always work with the space, because that's the only space we are going to use, obviously. So as you can see, even if I access the Nape API directly here to create the floor, because the floor has no visual representation and it doesn't update, so it doesn't need any component and doesn't need to be inside Genome2D. But I need to add the floor to the space of the Nape physics component. And our second component, also very simple, is a Nape body, which will initialize the boxes, obviously. So once this component is created, it creates a body, dynamic body with a box polygon, and once again adds it to the space of the Nape physics component. As you can see, we added the physics component to root. I always said that you should never add component to root, but this is great example of when you could and probably should do that, because there will only be one physics component, and what's more, it needs to be created as the first component, because it needs to be the first one that hooks the update handler. Because if you had for example created some boxes before you created this physics, they would update before the physics, and this update handler would be one step behind, one frame behind. So what this Nape body component does is basically again just hooks the update callback and updates the actual node transformations to the body positions and transformations, rotation and stuff like that. And if you want to move, let's say we create the box here. It's very simple. We create a box as a simple node with the Nape body component, then add the sprite component to the same node where we have the Nape body component, add the create texture, and then move the box to the mouse click position. All the falling and stuff like that, that's up to Nape to calculate the gravity, and we are no longer moving the node. But what we do here, we don't use something like this, box node transform x, because if it did this, we would move the node but not the body. Once we have the body there, the physics body, we need to move the physics body and let the Nape body component to invalidate the actual node position to the body position. That's why I set these setters here to redirect the. I could easily do something like this. I make the body public and save it. So if you could, this would be probably even faster if you don't inline the setters, but it's the same thing. In old Genome2D, this was handled by the transform, which knew, due to the abstract layer, which knew that there is a body on the transform. So if you did the node box node transform y, it knew that there is a body there, and it should set the body position as well, not just the node position. But again, it was inside the G-transform component and it was not that transparent, so I think this is a better solution. So people know when the physics is updated, and the code is absolutely transparent as well. Another thing there was inside the old Genome2D, there was that the body was on the space only when the node was in the render graph. So easily again we can do something like this. Is on stage. If the body is on stage, we will set the body space, body to the Nape space, and then we add a couple of more callbacks, such as this. I know I should probably use the auto generation, but I'm too lazy even to do that. So, and now if we add the node to the render graph, it should automatically add the body to the space, and once we remove it from the render graph or from the stage, it should remove the body from the stage as well, from the space. Simple as that. And it's clear all in this one simple component. We have the physics invalidation, which was before us through the abstract layer inside transform. We have this, which was before through the abstract layer inside the Genome code. So I think this is better. Some people may say that, for example, these updates, this add and remove updates, they are negligible because we are not going to add and remove a lot of nodes. This update handler is slower than the inside Genome2D abstract layer. I am not so sure because the layer was abstract, so there was no way to inline it. We can't inline this as well, but there was some kind of explicit casting needed as well, and we could easily do this through without the update here and do some kind of update and then add these components to the Nape physics component and have some kind of array of bodies that are or nodes that need to be invalidated, and we can inline that. For example, if we were some kind of optimization tricks needed, but I don't think they will be needed because there is not the physics overhead is so large that some kind of update callback is negligible in comparison. And that's all for Nape physics. We could do a lot of other things that could be added here, but it's up to you. This is something like a helper. This is the layer for manipulating with physics through Genome2D. So this single method is the main method that needs to be done because that's what reflects the changes in physics inside the Genome2D, and all the other stuff is just fancy stuff that could be done through Nape directly or in other ways not Genome2D related. So I hope you like it, and it's pretty easy to grasp. The next build will have all the abstract stuff cleaned inside Genome2D and inside both sources, Hexi and ActionScript sources. So it will be more readable, and I will also publish these Nape components to the as you can see, I use ActionScript, so they will be published to the ActionScript GitHub codebase as extensions. You will obviously need Nape library to work with Nape, and it will be not compiled into Genome2D. And you can compile it if you use Hexi, and if you want to compile the whole Genome2D and with Nape together, great. It will probably be even more performant due to inlining. Anyway, enjoy, and now let's move to the second topic of our DevCast, and that is custom renderers. What's a renderer? A renderer is something that actually renders, obviously, stuff. So it's the lowest level of code, because that's the code that actually calls the vertex buffer in validation index buffer, the draw triangles and all that stuff. So it's the lowest level of the rendering pipeline, and if you want now, you can create your own. For example, you want to render 3D objects inside Genome2D, you can do that through custom renderer easily. You will need to enable that buffer and stuff like that, but you can do that inside the custom renderer. So what do you need to create a custom renderer? There is an interface inside Genome2D, very simple interface with 3 methods that you will need to implement. First method is the bind method with 2 parameters. First parameter is the context. Oh, this is wrong. It should be context, and it will give you the instance to the Genome2D context, obviously. And second parameter is reinitialize, which is true when there was a lost context in the previous frame or in this frame, and it will tell you that the Genome2D is in the middle of context reinitialization. So if you for example create your which you will obviously create your vertex buffers or any GPU structures in your renderer, you will know that now there is a reinitialization, and you will need to recreate them and shaders and stuff like that. The second method is push method, which is always called when there is a different renderer going to be bound to the pipeline. For example, because some renderers will have empty push method as you see, but some renderers accumulate stuff before they draw it. For example, batching renderers. So if there is a switch to different renderer, for example, from simple call to matrix call, which use 2 different renderers inside Genome2D, if we bind the matrix renderer, the old renderer will need to push everything it accumulated but didn't draw yet and draw it to the screen, because otherwise we would end in the middle of the batch, and the stuff would not draw, because there would be a different renderer and different shaders and stuff like that. And the last method is clear, that will need to be implemented, and clear is also called when there is a different renderer and at the end of the frame, for example, but it's different because clears the GPU stuff, for example, bound textures and bound vertex buffers, because for example, if you bind 3 vertex buffers and the next renderer only needs 2 vertex buffer, and you didn't clear the 3, the next renderer wouldn't be able to render stuff, because there would be a third vertex buffer, and Eagle and Stage 3D would complain, obviously, and the renderer didn't know, the next renderer doesn't know that there is a third vertex buffer from previous render, obviously. But this clears stuff, push doesn't clear stuff, because sometimes you don't need, for example, push is always called after each batch, and you don't need to clear the GPU structures, because they will be reused for the next batch and next batch. So that's the difference between push and clear. And yeah, that's it. You will only need these three methods. So let's show you a simple renderer. This is rendered through custom renderer. It's a rotating quad, but it could be any shape. I'm just lazy to create a custom shape. And what we have here is a array of vertices. I will explain the Z later. And array of UVs. And we will create a custom renderer using the vertices and the UVs. And then here in our post render callback, what we do is bind. This is the most important method, bind the renderer, and then using the draw. So if you, let's say you created some custom renderers and stuff, and you want to render them, you can just call the custom with the custom render instance the draw method on the custom renderer, because it's not bound to the Genome2D, and Genome2D doesn't know that it will render using that custom renderer. And if you call just this draw, it wouldn't it wouldn't work. It would fight with the currently bound renderer. So what this does is tells Genome2D that it needs to clear the previous renderer. Obviously, for example, if we are in the middle of batch, it will flush the renderer and it will flush the batch to the screen. It will also clear the GPU structures that the previous renderer bound. For example, as I said, the vertex buffers, or there could be, for example, multiple textures bound, and it will clear them. So you don't need to think about, yeah, what if the previous renderer didn't clear the texture at the third texture sampler. So this will bind the renderer to the Genome2D pipeline, and once it's done, you can call the draw method on it. As you can see, there is no draw method inside the interface. This is because you can have any draw method. Most renderers have custom draw methods, not just texture as I have here, but they have like 20 parameters easily with all the position, colors, filters, and stuff like that. We're going to talk about what we are doing here. So let's look at the custom renderer. It's not very simple, but low level stuff rarely is. So what we have here is vertex shader code. For example, for our vertex shader, obviously. And okay, let's talk about the method. So we will go back to the once we encounter the variable. I will tell you what it is. So what the constructor has here is vertices, UVs, and generate perspective matrix. Vertices, as I said, we are creating a quad, simple quad, and with simple UVs, 0, 1 UVs. So what we create here is a transformation matrix, because this renderer we will not use position and stuff like that. It will use matrix directly, so we are initializing the matrix. It will be always used. Let's skip this projection for later, and we store the vertices and UVs internally. Now, as I said, there is this bind method that is called every time a renderer is binned to the Genome2D pipeline. So once this bind is called, what we do here, we check that if the G2D program, which is our shader program, is initialized. If it's not, we will call the initialize method. We could check this through, for example, checking the vertex buffer or the index buffer. It doesn't matter. We just need to check if our GPU structures are ready. If there are not, we call the initialize, and this is where the magic happens to create all our needed GPU structures. So we create the shader, vertex shader, we create the program for it. As you can see, I am using renderers common, which I'm not going to talk about that, to create the fragment shader, because a lot of renderers have the similar or the same fragment shaders than the others. So you can check this in the documentation. It will tell you that just give me the texture shader code for non-repeating linear I don't know, no, without map, no ATF, and no filter fragment code. Simple as that. Now we are going to again skip this projection matrix, and we are going to create the vertex buffer using the vertices and UV data we sent here, and upload them to the vertex buffer. We store this because we need it for context loss, and we could easily just store the vertex vector that we are creating here, but it's better to store it. I like it more like that. So again, we created the vertex buffer, and again, very simple index buffer that just consecutive indices, and upload it to the index buffer. And again, here I forgot to mention that we also check that there was not context loss. So we call this initialize where there is no GPU structures, which is when at the start of the Genome2D, or if there was a context loss. Because if there was a context loss, these GPU structures are not valid, but they are there, so this program will not be null. So this tells us that there was a context loss, and we need to reinitialize this. And what this G2D initialize this frame tells us is that we already did this frame, because Genome2D, if it lose context, it will tell all the shaders, all the renderers during this frame that there was a context loss. But for example, we can bind this renderer 2 or 3 times during the same frame. So the Genome2D will tell us 3 times, all the 3 times that we bind this renderer, that there was a context loss on this on the global instance of the context 3D, and it will always tell us that it's true. But so if we check it here, and we will call bind on this instance multiple times during this frame, this will already be true, so we don't need to reinitialize it. If it was reinitialized during this frame. And we set the program, GPU program. That's all we need to do inside bind. Most renderers have very complex bind, but this is very simple. I kept it simple without filters and stuff like that. So what we do here is our next method is draw. Again, very simple. We get the native context. I could easily do some stuff like this, because as you can see, I'm using Hexi, and this is all inlined. But for all the action scripters out there that don't use inline or can't use inline, because inline is somewhat buggy in ActionScript, you should always pre-store to local variable or even to global variable generated context. So again, skipping the projection metrics, and what we do here is set the texture, set the transform metrics to vertex constants, set the UVs to vertex constants. Never, and I repeat, never do it like this. This is just for this demo, but creating vectors per draw method call is like, I mean, this is memory overhead and allocation, deallocation hell. There should be, this vector should be some variable, class variable, and we should use it like this, texture wakes and set. So there is only one vector initialized once for this class, and then it's just set. But since I just wanted it simple, I create new vector for each of these draw calls, which is a optimization hell. Now we set the vertex buffer, first vertex buffer, which is our vertices, and second vertex buffer, which is our UVs. As you can see, we are working them with the shader, model viewer matrix, projection matrix, which is our camera matrix as well. Calculate the UV and send them to the fragment shader. And finally, we are calling draw triangles using the index buffer and the amount of draw triangle counts that we calculated from the UVs, obviously, from the vertices. Now, as you can see, there is the push method, which is empty, because as I said, it will be the Genome2D needs it, because batching renderers have draw triangles inside the push instead of inside the draw, because they accumulate stuff and draw them only when the batch is full. So since this custom renderer doesn't use any batching, we could do custom batching, for example, custom renderers. Anyone is free to do that. So you would have the draw triangles here. Just check if it's full and call push from draw if it's needed. So it's empty, but it will be called by Genome2D if needed. So, and the last one is the clear method, which is again called by Genome2D once the renderer needs to be cleared. So we clear the texture sampler, we clear the vertex buffer, and again projection metrics that I will skip for now. So since our renderer use the metrics, and I didn't didn't work with it inside the renderer, because for example if I want to draw this, as you can see I'm drawing the rectangle at 300 to the middle, 300 200 to the middle of the screen, but there is no position in the draw call and nowhere inside the renderer. I didn't add it here to work with the position to keep it the renderer simple, but we are having the transform matrix public, so we are working on it directly here in the main method, which is just for this example purposes. So we will clear it each frame and prepend our rotation around the z-axis and move it to the middle of the screen. Simple as that. That's why it's there where it is, because that's the model view matrix inside the vertex shader. Now we can easily rotate it around the y-axis, so actually in 3D. But as you can see, we are using the orthogonal matrix, which is the default matrix for any 2D renderer, even for Genome2D obviously. So it will rotate, but there is no perspective distortion. What we can do, and I did in this custom renderer just to show off the possibilities, is the projection matrix that I skipped during the examination of the code. So when we tell this renderer that we want this true, which will generate a custom projection matrix for us, we set it to true, and it will be used inside the vertex shader instead of the internal Genome2D matrix. So what it does is generate the perspective matrix from the context. You can, as you can see, it's public, so you could play with it and create your custom projection crazy matrices if you want, but it will create the best, for what I think is the best right now, matrix for projection, and that is using the ratio of width and height, and the far plane is twice the context height. I will tell you why later. And here in our draw method, it will check that if we have the custom projection matrix, it will set it to the constant 0. Constant 0 is very important inside Genome2D, because vertex constant 0 is always the projection matrix. Always, all the shaders, all the renderers use vertex constant 0 as a projection matrix, or camera matrix, let's say, because camera is just the additional transformation on the projection matrix. So that's why we here during clear need to, if we were using projection matrix, we need to set it to the active camera matrix. So if you use custom projection matrix, you basically using custom camera. So if you have the camera transformations somewhat, you will not have them in the custom projection. You can easily get it like here and add it to the projection matrix, but you need to know that once you override the 0 constant inside vertex shader, it's where is the projection, the default orthogonal projection with camera. And let's go back to this vertex initialization. Why I have depth as a z parameter? It doesn't matter if we are using orthogonal, because depth doesn't affect orthogonal projection. But if we are using perspective projection, the depth matters obviously, because if we had shallow depth, it would be large. And so I figured out that best depth is the actual height of the stage, because if we initialize the ratio for the perspective matrix like this and set the vertices to the depth of the height, it will have 1-to-1 obviously So 1 pixel will be 1 pixel in projection, which is not always the case if people play with projection. And that's why I also set the far plane to height, 2 times the height, because if we set the far plane only to the height, we would lose it. For example, if you rotated it, the pixels during the rotation would go outside of the far plane. Anyway, now if we run this with the rotation, we will get the perspective like that easily, which is very nice. Again, as I said, if I initialize the far plane to the 600 in our case, we would lose the half of the rectangle, since it would be outside of the far plane. And as you can see, there is this little line here, which, because we initialize the projection to the center of the screen, because if we initialize it top left, here, the rotation would look different, because the projection, it's hard to explain, I don't know how, because if the projection center was here, now it's here, as you can see, it's going into the infinity there, and the projection is, I don't know how to explain that, but if you initialize projection, if you play with the metrics, projection metrics, I initialize the projection center here, you will see that all the lines go like that, not like this. You get my point. So that's why we need to always append this translation to have the Flash native coordinate system from top left. Okay, I hope I didn't confuse you, to say the least, and you will enjoy playing with this. You can also, for example, once we are playing with matrices, you can actually know if you transform vector, if you use the custom transform matrix, transform vectors, or vectors probably, to in and out for this array, we will get the transformed vertices, which can be used, for example, for mouse detection. So you can also detect clicks and stuff like that. Even though if we are playing only with rectangles, I think that the raycast to the rotated plane would be faster, because once we do the raycast to the rotated plane, we are actually working again in ortho. So once we have the point of the rotated plane that the ray hit, we can just check with the with the orthogonal coordinate system. Anyway, so this is how we create custom renderers, and we can implement 3D stuff. You can even implement, there is nothing just holding you from creating, for example, some statue, full 3D object that will be rendered using this. I mean, it's possible, but you will need to obviously enable depth buffer for even if you have 2 of these 2D planes rotating and you want them intersecting, you should enable the buffer, but watch out for alpha. And I will play with these custom renderers later. For example, I'm preparing a shape renderer, which we already have the polygon renderer inside Genome2D, but I am preparing the old shape renderer, which was you can cache the shape inside the renderer, and it will just use the pre-stored GPU structures. And I'm preparing a few other renderers that will be handy, I think. And keep in mind that this is just Flash, because this is such a low level that if you wanted to implement custom renderers in Java or in Lime, and that you will need different approach to this. There will be same interface and same thing, but all this internal, since we are working with Flash Display 3D, and this will only work for Flash targets. So if you implement custom renderer, you will need to implement it for all the other targets as well. Okay, I think that's all. Oh, some of you asked why there is no direct 3D for the existing nodes and sprites and stuff like that. It could be it would be possible, but it would add so much overhead to the stuff that doesn't use 2D 3D that I think it's a wrong move. If you want to implement it, I would advise you to create a custom component using these custom renderers as well, and just calculate it like that, because I don't think there is a need for some huge complex 3D stuff that would need some kind of streamlined pipeline or something like that. But because most of this 2D stuff is used for UIs, as I saw, and simple effects, so you can achieve this using the custom renderer. For example, in our solitaire game, I use this for card flipping, and it's very simple, because during the card flip I didn't need, for example, mouse effects. So mouse effects were working with the 2D without the projection and all that, and once you clicked it, it switched to the custom renderer and did these 3D transformations, and once it was done, it was back again in 2D and used the default pipeline. So you can easily switch between the renderers, obviously. And if you indeed need the mouse interaction, as I said, you can work with the transformed vertices, and it's very possible to implement. So that's all for today, and watch out for the updates on GitHub. I will also update this weekend. I will update the Genome2D to new build, which uses the EG renderer, because now if you are using current version, there is no EG renderer, there is EG material. All these renderers were materials. For example, this is one. So that's because from my old 3D engine, I use the material for as the name for these structures, and now I think it's more appropriate to use a renderer name. So there will be a cleanup for these materials and renderers. There will be cleanup of the physics in the new version, so watch out for that. I will update the Nape physics there as well, and a few other new features in Genome2D that I'm not going to talk about it, because I don't know how I will be able to finish it. For example, the shape caching and new post processes, new filters and stuff like that. So that's all, folks, and let me know what you think, and any suggestions for future devcasts are welcome as well, and thank you.